Okay, so in this numerical example, which is taken from the R.C. Hibbeler book, so a 10 kilogram rectangular plate shown in this figure here is suspended its center from the rod having a torsional stiffness K equal this. So stiffness is given in this case, which is 1.5 Newton meter per radian, because this is a torsional stiffness. Determine the natural period of vibration of the plate when it is given a small angular displacement theta in the plane of the plate. So if you displace this plate using this sort of motion here, so if you give it a torsional vibration, it will start to vibrate in this plane here. So it will just start to vibrate like this. Okay, so in this case, as you can see that the displacement is positive in this direction here. We're taking this displacement is positive, or angular displacement. So this means that the theta double dot, which is the angular acceleration, will also be positive in this direction here. Okay, so now what else you are given is the mass is given, which is 10 kilogram, and stiffness is given, and you need to calculate determine the natural period of vibration. So you need to calculate the tau here. Okay, so in this case, again we will first write the equation of motion for this system here. Now we already derived the equation of motion for the spring and mass system, but this is now a system with the angular motion. So in this case, again, we will use the Newton's second law, summation of all the moments about O is equal to I naught theta double dot. So which is again the summation of all the which is summation of all the forces equal to mx double dot. So this was the equation for the linear motion. Now we will replace this F by moment or torques, and then m by moment of inertia, and x double dot by theta double dot, which is angular acceleration here. Okay, so now we know that in this case, uh, the if you displace this body in this direction here, so uh, the sort of spring moment or the restoring moment will be in opposite to this direction here, and in this case obviously it will be equal to k theta, because we know that f is equal to kx. So then m will become equal to k, which is the so k in this case is the torsional stiffness, and we will replace the linear displacement, which is x, by the angular displacement, which is theta. In this case, the moment will become equal to k theta, and we know that this is opposite to the acceleration here. So if you want to write the equation here, so this will become equal to minus k theta equal to I naught theta double dot here. So you can simplify this equation. So I naught theta double dot plus k theta equals 0, or theta double dot plus k divided by I naught theta equals 0. Now we know that the x double dot plus omega n square x equals 0. We know that we derive this equation in case of linear motion. Now if we compare these two equations, so this is our equation 1 and this is equation 2. Equations 1 and 2. We can say that omega n will be equal to k divided by I naught under the root. So this is our natural frequency for this specific case. And If you want to calculate this I naught here, you can also calculate its value, because we already derived this in the previous case, that we know the equation of I naught. So if you I naught for this case is equal to 1 over 12 m a square plus b square. So you can find this in the table in the angular motion lecture. The table was given, and it's also, the table is also given in the formula sheet. So you can see that uh, the moment of inertia of this block from its center is equal to 1 over 12 m a square plus b square. And because now we know the value of m and a and b, so if you put the values, you will get this is your moment of inertia here. Okay, so now you can calculate from here omega n, or you can calculate the natural frequency in fn. So you will just divide this by 1 over 2 pi. So it should become equal to k I naught. This is the natural frequency in this case. And you can also calculate tau here. So tau, we know that it is just 1 over fn, and which is what we need to calculate here. So which will become equal to 2 pi I naught divided by k. This is the time period. So if you just put the values here, so 2 pi and then 0.1083 divided by k, which is 1.5 under the root. So tau will become equal to 1.69 seconds here.